To prove an implication if P then Q, we can use contraposition. The contrapositive of if P then Q is if not Q, then not P. Both statements are logically equivalent, so we can say that this is equivalent to this. So proving one is as good as proving the other. Here's the method we're going to use. First, we will state that we prove the contrapositive. It is always a good practice to state what kind of proof you're using. Second, we are going to assume not Q. Third, we will show that given not Q, not P follows. And finally, we will conclude that the original implication then holds, due to the logical equivalence between this original implication and the contrapositive. Let's write again our contrapositive here. So not Q implies not P. And let's see an example. Let's prove the theorem, if R is irrational, then the square root of R is also irrational. If we try to prove this directly, we're going to run into a problem, so a contrapositive proof is useful here. First, is this an implication? Yes, it is. We have an if P, which is R is irrational, then Q, which is the square root of R, is also irrational. So here our P, let's state that, is R is irrational. And our Q is the square root of R is irrational. Now let's follow our method. First, let's state that we prove the contrapositive. So I'll write proof by contraposition. Then let's assume not Q. Q is the square root of R is irrational. What is the negation of that? The negation of the square root of a number is irrational, is the square root of that number is rational. So we will assume that the square root of R is rational, but how can we write a number in an explicit rational form? Well, if square root of R is rational, then it can be written as m over n, where m and n are both integers. And also, n must not be 0, otherwise we would have a division by 0. So that's our second step. Now, third step, show that not P follows. Let's square both sides of this equation. Then we get R equals m squared over n squared. Well, if m and n are integers, both m squared and n squared must also be integers, because if you square any integer, you get another integer. So we can conclude that R is rational. And what is this? It's not P. It's the negation of the antecedent of our original implication. So we have assumed not Q, and this showed us that not P follows as per the third step of our method. And by the definition of the contrapositive, this leads us to conclude that the original implication holds, so P does imply Q, and our proof is done.